All right, then in the past two sections of this course, we've looked at basically the theory of power factor, where it comes from in the AC circuits, how does it really impact the EVs, and then we looked at a little bit of topology of how a totem pole based power factor conversion or correction happens. So now it's a little bit of fun that we're going to have. So it'll be more of a practical section of this course. So we'll be using Matlab Simulink to build a totem pole converter. So let's get started. Okay, so as discussed in the previous chapter, so if you had a look on the circuit diagram, so we can have basically just two poles, basically, as the name derives itself from the totem pole. So we can just have two legs. So one is a high frequency leg and one is a low frequency leg. So for the high frequency leg, we will be using the Mosfets, and for the low frequency leg, we'll be using just the diodes. But to improve the efficiency, it can be all four as Mosfets. Also, I'll be explaining why is it going to be a low frequency and a high frequency leg during the simulation. Okay, so let's get started with Mosfet. Mosfet. Okay, so we're gonna have the drain and the source like this. So we're gonna replicate this once again. And then we will have two diodes. Okay, so that's going to be the four elements in our totem pole topology. So then we shall have an AC voltage. I'm just looking for the one with SimScape, without SimScape. Okay, this one should work. All right, so specialized tools. Okay, so now we're gonna build one inductor. Okay, now we can select it here just as an inductor. Okay, so should be good. then we should be able to, so the strategy is basically that we should be able to control the current through this inductor. So we should force the current to this inductor in such a way that it follows the voltage. So for that, we need to have a current measurement. So current measurements always in series. I'm gonna connect it like this. Okay, so here we have the source and the drain. So we connect the source with the drain, and here as well. Connect this to this. That's correct. And so this terminal is for, let's say, the scope, and this is for the actual connection. So it goes in here. And the written path for the AC, so this is the source, and the written goes in here. Okay. So then we completed, so the drain is connected to this, and the source is connected to this. Okay, so that's the fundamental. So then we will have, let's say, another load connected, series RLC branch. So yeah, let's have a resistive. Okay, maybe 12 ohms. Okay. Then we also have a link, DC link capacitor. This is very important. Now it should be at least 80 micro. Okay. Okay, now we have it here, so we close the loop. So we will also add one more current measurement here, because we would like to know what is the current going into our load. Right. Okay. So we shall also have a voltage measurement, most important thing. So voltage measurement. So it goes in here. So across the voltage source. Yeah. So the two most important things is this voltage source and this current source. So these are going to be our sensors, so to say, to implement this power factor correction. Okay, so now that we have built the basic power electronics, so we will start building the control strategy, basically. So we have, so we're going to name our current measurements. Let's put a go-to block. Let's name it IL, so the current through the inductor, no matching block, that's okay. So we take it out. We have it here. So then here we put again a go-to block. This is going to be Vin, right? So basically what we're gonna do is all right. So now going back to the drawing board again. So there are two ways you would want to control it. So first thing is you also want to control the amplitude of the output. So if you want, for example, most of the current generation of electric vehicles use a 400 volt DC battery, while also upcoming generations use 800 volt DC battery. So let's consider this as a 400 volt DC model. So because essentially what we are trying to say is this is, let's say, your AC source, which is coming from the EVSE, coming from the wall box, coming from any AC source. So now once this is going through the PFC, so there are two things which is going to happen. So one thing is the AC to DC rectification, which happens in a single stage, and also during the single stage, the power factor correction also happens. So this is the main advantage of having a totem pole configuration rather than having something like a double boost configuration. So normally in a double boost configurations, you are having two stages of power factor conversion as well as at the AC to DC rectification. So that's the advantage of this. So you only have four switches here, and then you will have pretty much the rectification as well as the power factor correction happening at the same. So having said that, so we are going to target 400 volts here, which is on the I out. So let's put this as my I out. Okay. So, all right. So if we have 12 ohms, or for example 10 ohms, it's going to have something like 40 amperes. Okay, so now let's get to building the actual control strategy. Yeah. So I said it's going to be a dual PI loop controlled strategy. So we're going to control the voltage, 400 volts, and we are also going to control the power factor, right? So for that, how do we do it? So before that, let me also give this. So let's put for the gate. So let's say this is my S1, which is going to be the gate pulses. Okay, so I should do this first. So you got to be careful when selecting the go-to blocks. So this is my source, so you should always see that. So since I have only two Mosfets, I will only have two gate signals. Go to, let's put it as S2. Check it out. So this goes in here. All right, so now we have here. Okay, that should be enough of a space. Okay, so we said 400 volts should be our output. So let's create a constant here. Constant, let's put it 400. And let's also give us our AC, for example, 230 volts, 50 hertz. It should be on. Okay, so 400 volt, then So next we are going to give the reference. So we also need a voltage measurement here. Voltage measurement. So let's put that as V out. Okay, so I was looking for this. Alright, so it's going to be plus and minus, so we are basically taking the error out of it. So 400 is our reference, then what is coming out of V will be the closed loop information. So V out goes in here, whatever is the error will go through a PI block. So you got to select PID. However, you have the option to select PI. So there is a reason why this is done. So normally if you have a PID, so derivative, so what it does is it's basically taking the difference of the error with respect to the time. And what happens is if you have a noisy situation that you're having a lot of spikes in your voltage measurements or so on, so the derivative element is going to create huge values. So it's generally preferred to have a simple PI controller to have a more um, uh, steady state response. But if you really want to have, for example, um, a PID controller which is trying to control the way um, a ball is bouncing on a disk. So in that case, you need to be very, very quick and precise in how do you want to control it. So in that case, steady state controllers are not the best case, but you need to have really fast action or fast acting controllers. So that's where you need PIDs, but for us, PI is the best. Okay, and then after the PI, so typically you would want to have a saturation. So that's because normally PI is based on the constants that we give for the proportional and the integral. The values can range from anywhere to anywhere, basically. So we can have instead, we just put it from minus 0.5 to plus, or minus 1 to plus 1. That will keep our references quite easy. All right, so then what we are going to do is, now that we have a reference of what is the difference in the voltage, so we're going to multiply it with the V reference, right?